Today we'll start talking about the confidence intervals for proportions, and this starts on page 125 in the blue book. What I'm going to talk about first is a prelude to that, so I didn't leave a space to write that. So if you're looking for a place in the blue book to put these notes, you could write this on page 126. Before break, we were talking about the central limit theorem, or as I called it, the land of unreality. This is where we knew the true parameter, so in this case we know the true proportion, and we took many samples. And the central limit theorem told us that when we have a population and we know the true percentage, and we take many samples, that because we know that those sample percentages are normally distributed around the true percentage, if we go out 1.96 standard errors in both directions, that we can say that we expect that 95% of the sample percentages will be in this range. It's now time to cross over to the land of reality. Usually this is cause for great rejoicing, but this semester maybe not so much. I think maybe none of us would mind going back to the land of unreality where we were a month ago. But we will get through this. In the land of reality, we do not know the true parameter, or in this case, the true proportion. We take one sample, and we have one sample percentage that we're going to use to estimate the true percentage. Is just turn that problem around. So what we're going to say is similar to saying, well, if you're 6 feet away from me, then I'm 6 feet away from you because, naturally we're social distancing. So if we go out 1.96 standard errors in either direction, we can be 95% confident that the true percentage is in this range. So back when we were talking about the central limit theorem, we can use the word probability, okay? In other words, we could say that 95% of the sample percentages will be in this range. Now, in the land of reality, we cannot use the word probability. So instead, we use the word confidence, and we're going to talk more about why that is on a future slide. So now I'm back on page 125, and all confidence intervals follow the same general form. You have your statistic plus and minus your margin of error, where the margin of error equals some multiplier times the standard error. So you start with your statistic, and that is at the center of the interval. To that, you're going to add the margin of error, and I'm using the notation M with a subscript of E to stand for margin of error. And you're going to subtract the margin of error. This will give you two endpoints, okay, which will form your interval. So that's the general form for all confidence intervals. And so let's see what that looks like for proportions. So first of all, p hat, the sample percentage, is our statistic. So as we said on the previous page, p hat, the sample percentage, is normally distributed around p, the population percentage, and the standard error that measures the dispersion of p hat around p is square root of p times 1 minus p over n. And here's where we have a problem. We're in the land of reality now, and we don't know p, the true population percentage. So what is plan B? That's the statistics plan B, not the kind you get at the drugstore. Estimate it with the sample percentage. That's great, Chip. That's exactly what we're going to do. We're going to take those p's and just add hats to them. And then this is going to be an estimated standard error because we're using estimates of p. So here's our estimated standard error. And since p hat, and that should be a hat on there, is normally distributed, okay, the multiplier that we're going to use is going to be z star from our normal distribution. And that gives us this for our margin of error. And putting that all together, we have our statistic plus and minus our margin of error equals this expression right here. So that's our confidence interval. This piece right here, the plus minus piece, is the margin of error. So now I'm on page 127, and this right here is the formula we just had on the previous page up there for our reference, so we can use it to do some examples now. And this example comes from the Gallup poll taken just March 20 to 22, just last week, which already feels like a month ago. And I'm sure you've all heard of Gallup poll, and I have to tell you that I've been teaching this class or a version of it for almost 30 years, and in all those years I've always used Gallup poll in at least a couple examples, but I've never ever been called by the Gallup poll until last semester, and I hardly ever even pick up the phone if I don't recognize the caller, but for some reason I did, and it was the Gallup poll, and they said, "This is the Gallup poll. Would you be willing to answer a few questions this evening?" And I said, "Yes!" And the guy was kind of taken aback because I'm sure that's the response he gets, like, never. But I think he was quite happy that he finally had somebody that was excited to answer his questions instead of hanging up on him. So obviously all the questions they asked last week were related to COVID-19, and this question was about social distancing, and specifically the question was, in the last week, have you been avoiding small gatherings with friends and family? 68% said yes. Let's assume for now that they had a simple random sample of 1,000. So for givens, we have p hat equals 0.68 and n equals 1,000. Okay, so p hat coming from the percentage that said yes, and that's our sample size. Let's start by finding a 90% confidence interval. Okay, so when we look up at our formula up here, we have our p hat, we have our n, and all we need is our z star, which we'll get from our normal distribution. This 90% is called the confidence level, and that is the area in the middle of the normal distribution. So if we have 90% in the middle, that means we have 5% on each tail, and we can either look up the 5th percentile on the negative side or look up 95% on the positive side, and in either case we will find that z star equals 1.645, one that we pretty much know by now without looking it up. So our 90% confidence interval for p, and CI is my abbreviation for confidence interval, and plugging all our givens and our z star into our formula gives us this equation right here. The plus minus piece is our margin of error, which gives us a final answer of 0.6557 to 0.7043, or 65.57% to 70.43%. Of course, in WebAssign, like always, we'll be using the decimal versions. So for part B, let's find a 95% confidence interval for P, the true percentage. And when we have 95% in the middle, Z star is 1.96. And we can plug all that into our formula, which is going to give us, which gives us 0.68 plus or minus 0.0289. And if we round that for the sake of simplicity, that gives us a margin of error of 3%. So the formula looks almost exactly like what we were doing before spring break. The only difference is that our P's and our P hats are switched. So you've already mastered doing the calculations. What's different is the interpretation. The interpretation is that we can be 95% confident that the true percentage of those avoiding small gatherings is between 65 and 71%. So this is not the same as saying that there's a 95% probability that the true percentage is between 65 and 71%. So it seems like a subtle difference in our language here. We're confident that it's in that range, not saying that there's a probability it's in that range. And so we'll come back to this idea on a later slide. So now they actually used a sample size of 3,555 U.S. adults, and they're weighting the samples to correct for non-response. And they still have a margin of error of plus or minus 3 percentage points. So that's our margin of error, which it says. So what they did is they kept their margin of error at 3%, and how they did that was that they're now taking samples that are 3.5 times the size that they used to be. So next I'd like to do this example on page 128. This data comes from the Pew Research 2018 social media study. And the data right down here is the data they collected on Twitter usage by age group. So what we can do is find a confidence interval for the true percentage of Twitter users for each age group separately. So find a 95% confidence interval for the true percentage of Twitter users in each age group, and I'm going to start with my own age group of 50 to 64-year-olds. Okay, and our givens are N from our sample size of 55 and P hat from the sample percentage of 0.19, and we also know that our confidence level is 95%. I'm just using CL to stand for confidence level. And that confidence level of 95% is one that we should have memorized already, and that tells us that our Z star is going to be 1.96, because we know that 95% of the area under the normal curve is between plus and minus 1.96 standard errors. So using our formula, P confidence interval for P equals P hat plus or minus Z star times the standard error gives us 0.19 plus or minus 1.96 times square root of 0.19 times 1 minus 0.19 all over 55. And we plug that in our calculator. That's going to give us 0.19 plus or minus 0.1037. And I'm going to round that for purposes of working this out on the board to plus or minus 0.1 or 10%. So just a reminder for WebAssign, still go out to 4 decimal places. And that gives us a final interval of 0.09 to 0.29. Okay, so that tells us we can be 95% confident that the true percentage of 50 to 64-year-olds that use Twitter is between 9% and 29%. So at this point, you should pause the video work this out for, do a similar confidence interval for your own age group. For most of you, that would be 18 to 24-year-olds. And unless we already did your age group, in which case you can just pick one of those age groups. So pause the video here and work through the math for one of these other age. So the math for the 18 to 24-year-olds, when you plug everything in, comes out to 0.45 plus or minus 0.07 for a margin of error, or an interval between 0.38 and 0.52, or in other words, we can be 95% confident that the true percentage of 18 to 24-year-olds using Twitter is between 38% and 52%. And our question now is, how do these intervals compare, and what conclusions can we draw based on that comparison? So let's put those confidence intervals on a graph so we can make a visual comparison. And I have 4 horizontal lines here. We can put each age group on one of the lines. So let's put 18 to 24 at the bottom line, and this can be for the 25 to 29 if anyone did that group, 30 to 49, or my age group up here that we worked out on the previous page, 50 to 64-year-olds. So on the oldest age group, we had a sample percentage of 0.19. Okay, so that's right there. And we said that went out to, so the sample percentage was 0.19. So that is at the center of the interval, somewhere right around there. And the lower end of the interval was at 0.09. And the upper end of the interval is at 0.29. So our interval is something like this. For the 18 to 24-year-olds, the sample percentage was 0.45, so that's at the center of the interval. And that one went down to 0.38 and up to 0.52. And I'm seeing that I could have stretched this interval out quite a bit here, so things weren't so cramped. Okay, now let's compare these two intervals. We can see that there's no overlap between these two intervals. Okay, the 50 to 64-year-olds, the highest point is 0.29, and that is lower than the lowest point on the 18 to 24-year-olds. So no overlap. And thus we can conclude that we can be 95% confident there is a true difference between these groups. Now on the next page, page 130, I have all the math here for all four groups so we can see what the other two groups look like, and I have the graph drawn more precisely because I did it with a computer. And so now let's compare our other two groups. Our 18 to 25-year-olds went from 0.26 up to 0.41, and the 30 to 49-year-olds, the center of the interval is at 0.25. So one thing to notice is the width of these intervals, okay? So notice how the oldest age group had a really wide interval because they had a small sample size compared to, for example, the 30 to 49-year-olds. That interval only went from 0.21 to 0.29. Margin of error on that was only 4% approximately. So on this one we have a large sample size of 528, gives us a narrow interval. So that's the effect of these two different sample sizes, 55 compared to like 528. The next thing to look at is, again, this overlapping. When we compare the 50 to 64-year-olds, these do overlap. So the true value for both of them could be somewhere in this overlapping region. So we cannot be 95% confident that there is a true difference in the percentage for these two groups. So we cannot be confident of a difference between the oldest and the next oldest, or the oldest and the 25 to 29, or this one from this one. So it looks like where we could be confident of a difference is between the youngest group only overlaps with the people in their 20s, okay? So that looks like there is a true difference between the oldest group and the middle age group and the youngest group. If the intervals overlap, we cannot be confident there is a true difference. And if intervals do not overlap, we can be confident there's a true difference. Oh, no, we're just doing P this week. Next week we'll be looking at mu. So on page 131 is instructions for doing an applet. In my other class, I had some problems this semester with the Rossman Chance applet, so I'm not sure if this will work for everybody. So I'm just going to skip that and go to page 132. And what we have here on page 132 is, this is kind of like having a foot in each land. So we're kind of taking a look, a look back across that river that we crossed, back to the land of unreality. And what these plots show is, well, what if we went and we did all those samples that we used to talk about, the many, many samples, and we did confidence intervals for each one, okay? Would those confidence intervals always capture the true parameter? So in this first panel, so back up for a second, all of these are for a true proportion or percentage of 50-50, okay? And the three different panels, this first one's for sample size of 30, then sample size of 100, and a sample size of 400. And each one of these lines represents a different one of our many, many samples and the confidence interval calculated from each one. The line down the middle is at 0.5, so that's the true value. So if we start here at the top, we see that this one, it's just actually touching the true value. All these contain the true value of 0.5, and so on until we actually get down to this one right here. It says, and to make it clear, bad 95%. This is a 95% confidence interval based on randomly chosen data. That's how I constructed these. And this one does not capture the true value. And we have another one here that does not capture the true value. So altogether on this one we have, there's 100 altogether. So on this one we have 3 out of 100. That are bad. Likewise on this one, this next one, we have 1, 2, 3, 4, 5, 6 out of 100 that are bad. And on this one over here, we have 1, 2, again, 3 bad ones. So we expect overall, if we did, thousands and thousands of these, that overall we would expect to get 5 bad ones out of every 100. And 95 or 95% will be good. Okay, so this is what the 95% confidence means. It means that if we choose all possible samples, 95% of those samples are going to give us a good 95% confidence interval. Okay, notice that what's the difference we see as our sample size changes? Okay, for 30, we have wider intervals, and 100, they get narrower, and as 400, they're even narrower still, especially compared to the 30. But in all cases, we still have approximately 95% of the intervals will be good, and 5% will be bad. So the 95% confidence is not saying that there's a 95% chance that the parameter is going to be somewhere in that interval. It's saying, well, no, 95% of the intervals are good. The parameter stays the same. Okay, this is why we don't talk about probability with regards to the parameters. Parameters the same. The probability is in whether or not you get a good sample. And just to clarify, By good interval, I mean the interval does include or capture the true percentage. And conversely, by a bad interval, I mean the interval does not include the true percentage. If we take many, many samples, or theoretically all possible samples, we know from the central limit theorem that 95% of the samples will be good in the sense that they capture the true value. This is where probability comes in. There is a 95% probability that we get a good sample, which is why we can say we are 95% confident that the true value is in the interval. If we use the word probability in connection with the true value, that would imply that it changes. The true value stays the same. It is the sample that changes. On the next page, if we start off, and this one's different because this one is actually a true value of p equals 10% compared to 50%. Our other one was right down the middle. And when we look at this really small sample size, how many bad ones? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 bad ones. Okay, we'll get up to a sample size of 100. Oh, now we have 2 bad ones. And a sample size of 400. We have 1, 2, 3, 4, 5 bad ones. Okay, that seems reasonable. So what's going on with this 19 bad ones? Okay, that a 95% confidence interval would have like 95% good, meaning we should expect around 5 bad ones. So what's happening here is that when we have n of 30 and p of 0.1, np equals 3, and the central limit theorem doesn't apply. The sample size is not large enough. Okay, so I'm going to let you read this page most. It's for the most part, this is all the things that we just got done saying on the previous page, just kind of up until this point. Key point of the confidence interval was approximately 95% of the 95% intervals contain the true percentage. I think in a previous edition I had those pages repeated for 99% confidence intervals, and on that we would have seen that approximately 99% of those were good. Likewise, for a 90% confidence interval, we'd expect 90% of them to be good. No, somebody else from your group asked that same question. So we'll be looking at mu next week. So at this point, you should do in-class exercise 15 on pages 50 to 51. And you can do in-class exercise 16A on page 52. This one's really like a pre-assignment for the discussion of the sample size calculations. I will make the answers to in-class exercise 15 available in WebAssign so that you can go ahead and start the new WebAssign, which is posted and which is due next week, Tuesday, April 7.